please go ahead. It's all yours.
Give me a second. Let me load up my slideshow. Can everyone see my screen?
Yes, please.
All right. So our project, the title for our project is a networkless protocol for real-time systems, made by Abhishek, Hadi, and me, Nishant. And we're going to start our presentation on that. Okay. So the problem statement is as this, right? So how to achieve a file transfer in a centralized networkless real-time system so that the file space in the central servers is optimized. Because if you have a real-time system, you'll get a constant stream of data all the time. And again, it's usually it's beneficial to drop that data. But if you think about it, in most machine learning models these days, having like that data might be useful. So our approach was to figure out how can we, make the centralized server hold more data and make it networkless at the same time. Moving on. So the key issues that we focused on, they're the 4 key issues that we focused on. The first one, of course, file transfer in a networkless environment. Second one was maintaining the robustness of the file system in case of data loss. The third one.
Sorry, I missed something probably from your first slide.
Yes.
What do you mean networkless environment?
When I say networkless environment, it's not connected to the internet, and all the information transfer is going to be done using a person. So a person actually goes ahead between client and the centralized server at least.
Got it. Okay, thank you.
So the key issues that we are focusing on are file transfer in a networkless system. Of course, that will have like an actual person doing that, but we also have a protocol regarding that. Maintaining the robustness of the file system in case of data loss. We don't focus too much on data loss, but we do want the system to be a bit less tolerant towards data loss, but not as much as TCP. The third issue that we are focusing on, of course, is maintaining the size requirements of the central server. By this, we mean, how much we can store or how to increase the output of the file that we're storing inside the central server. And again, the partial loss tolerance of files. Partial loss tolerance of files is a bit different from like data, maintaining the robustness. The robustness kind of focus on the file system on the central server, and the partial loss tolerance kind of focus on what happens if the packets drop. All right. So this is like our networkless file transfer protocol, or NLFTP. And the idea is very simple, right? The idea is that we are assuming the client is on a mobile system and is of course an application-based system. So once you start that application, the client will constantly start pinging the server, right? But will only get a response once it's in the radius of that, in that radius. And that is a function of time or distance, technically, speed and distance. So the client has to get close to the server enough so that it can do a Bluetooth communication. And we figured out that it's much easier, not much easier, but like it's much more beneficial for us to have like closer range than the maximum Bluetooth range, mainly because we want the strength to be, strong. And there are other servers around there. So we do not want like the Bluetooth files to be pinging everywhere else and like weakening the signal. And that just leads to congestion in the network. So again, like it says, client continuously queries the server on Bluetooth. Communication only starts when the client comes in the range of the server. And we implemented a simulation of this in our final project. And again, the communication, to hammer in point, the communication only happens if the client is in a range. So if the client kind of goes out of the range, the packets will start dropping. The whole idea is that when you're sending the packets, it only receives packets received in a certain time frame. After that, it will drop in saying like, hey, it's outside the range. It doesn't recognize that it's probably the server that it's talking to. It might be something else. So it just moves away. Any questions regarding that?
Yeah, so this is really a one hop transportation layer protocol,
yes.
Right?
Yes. Okay. And here's the actual protocol that we are doing. So in a real-time system, a user and client again, that's the idea behind here. In a real-time system, a user and client should be able to access the files in the central server. And in most popular systems, you could do that, but not to like, you cannot modify the files, readily. You have to like go up to, go to a cloud-based system and then do that. We are basically saying you can just use that. You can use your phone, access the server, and update the files that it's recording, because of course you don't know what the sensors are recording. And I feel like, and we all feel like you should have access to that data. The client, as mentioned before, queries the file. This is the file transfer protocol by itself that we are describing here. The client queries the server for file transfer, And the server then copies the file and sends the copy. The reason for copying the file is because since we are making it networkless and we are dependent on the person, and again, people are error prone, they might go out of the server range or might be barely in the server range. So it's not beneficial to send that one copy over the network or over the Bluetooth network, because you might lose that forever, or that file might get partially corrupted if you don't keep a copy. That's to preserve the robustness of our file system. So that kind of makes the whole thing partially loss tolerant because you have a backup every time. So yeah, if you kind of miss the packets, both sides just delete it and say like, hey, it never happened. And you can query again because it's a real-time system and the person is controlling the network or the communication at least. For changing the files, the full file has to be transferred before the original file gets changed. This is again to make sure the robustness of the file system is maintained. If this is not done, it's possible that a partial file is transferred in and then the overwrite happens, and then you have a partial file, and that just creates issues at the end because then you have corrupted data, and that will lead to, if there's a machine learning model running on the main system, well, that gets like, false data. And if it happens enough times, yeah.
A small question.
Yes.
When I'm going to change the file, can I just change the delta of the file, which saves network bandwidth?
Yes,
that's what I'm saying. Yeah.
That is more optimal. We weren't able to implement it. This is like in our future work. That's like you can have a delta.
Sure. Okay.
But yeah, that is much more optimal. That you are right. But yeah, any other questions?
No, this is good. I'm interested too, especially your bullet number 2. How do we actually provide a backup, or in this type of environment? I know you want to preserve the original, and then this kind of networkless environment, it might have some constraint about the faults that might happen. So depending on how you actually the infrastructure, but that's an interesting question. I will ask you later when I see the whole thing.
Then here are the functions that we're kind of implemented in our the final project presentation or the demo that we created. These are the functions that were already available to us. The dump that's more of a debugging tool to check everything's working all right. Lookup, again, it's already present in like the implementations that we already had. Lookup just checks for the file and creates a file. Now, to make the terminology a bit clear, the oval is the sensor server. The rectangle represents our main central server, and the other trapezium-like figure, that's our client. So the sensor server only sends the data. We haven't implemented that in our demo because that's the only thing it's doing. So it's pretty explanatory. Like if there's a concentration of data, we don't need to kind of simulate that. The central server has send and zip. Send basically pushes the data to the client in accordance to NLFTP that we just described. And zip compresses the data that it gets from either the client or the sensor function or the sensor server. The idea behind that is that the zip function will get it over there. And again, in the JSON file, we kind of specify that, hey, what type of file is it? And we're assuming that, you're going to use one of the zipping features to zip the file that we got. So for example, if you got the CSV data, you will have like...
Just clarify, which one is the client? Is it the client on the left or client on the right?
On my right. So the client is, if you can see my cursor, I'm like moving my cursor over there. That's the client.
Okay. Then what's on the right? What
on the right, that's
on the left, on your left.
On my left, that's the sensor server that's constantly pushing the data the sensor is collecting. We didn't want to give it too many functions because it's already collecting data. And again, that's where all the computational services should be, because if you start adding other things like zipping or doing anything else, that kind of stops the capturing of data from the sensor. And we personally felt like that's not exactly a good idea for the whole system.
Yeah, so let me just double check, because I think I misunderstood this part a little bit. So the one on the left, this oval shape,
yes,
you said that's the sensor.
Yes.
The sensor is collecting some kind of data from the environment, yes, I assume. And the rectangle in the middle is the central server.
Yes.
And then this, I don't know how to describe this shape. It's a little bit round on the left side. That's what you call the client.
Yes.
That's essentially your phone. Is that right? You talk about mobile device, and then
Yes.
from the networkless file transfer protocol is really between the center and the client.
Yes.
Sorry, on the server and the client. Yeah.
Yes.
Okay. All right. Thank you.
Yeah, but again, like we felt like it's not exactly efficient to create that between the sensor and the central server, because again, the person will have to move a lot more, and that's not exactly feasible for a person unless they want to walk as much. But yeah, we felt like we should keep it there because all the data you can access from the central server anyways. The function, moving on to the client has like, again, the create function and lookup function are already there. So we didn't bother creating them, but we did create an update function that can update and change the values inside the central server to give the client a bit more control over the data that, that's being collected about them. So again, the update function kind of accesses the file and, just sends a file back from the client to the server and says like, hey, update that part. And when we said like, when we're updating between client and server, the client will send that file and the server does not update until the full file has been transferred over, as opposed to, updating while the file is getting transferred, mainly because of the communication. If the communication drops because if the client moves out of the range, again, we might have a corrupted file, or even worse than that, non-correct file or partially changed file. So moving on, let me do a demo that we have prepared for this. Let me run my project, mini server. And
so while you're setting up, may I ask you a question? Because earlier you were talking about the client move within the range of the server, then you can start communicating. So essentially you're probing to see the distance. And there might be even a situation that a client might be able to, do you assume the client might be simultaneously closing the range to two different servers, but they have a choice depending on the signal strengths to see which central server I'm going to use? Or you're assuming there should be only one central server in that area? What's your assumption there?
We assume that there's only one central server. We base this assumption off like the current literature. Most centralized servers that we looked at were just using one central server, but that is actually some future work that we planned in, because that comes as a basic follow-up question, right? Like, what if there are two servers? What if the sensor server, is also communicating somehow and it's interfering with the communication? And what if there are two clients? But
because then you have to worry about the roaming issue as well.
Yes.
Well, the thing is, I'm thinking about the protocol. Usually the protocol, like a transport layer protocol, they set up the connection such as three-way handshake, and they kind of not move around. They kind of fix it. In your protocol, it's just, how will you consider the networkless compared to, say, the traditional three-way handshake? Are you going to do three-way handshake?
No, we are only doing a two-way handshake, actually. We discussed about this. The idea was that a three-way handshake would be, like you said, you're fixing the thing at one particular point. In our two-way handshake is that you send an acknowledgement, or at least the client's in the query, and again, it's probing, right? And once the probing has been done, the server gets you back, and that's it. Like the whole idea is there should be a connection now. It's a weaker connection of TCP. We base it off TCP, actually. We were like, the three-way connection might not be possible because of a moving client. But if you are doing a two-way connection, we can kind of guarantee that, hey, there might be a connection, as opposed to there is a guaranteed connection.
I see. Okay. All right.
Let me show you the demo. I think it might have finished running by this point. We had like a whole time thing. But yeah, can you see this screen? Like,
yes.
So if you start from the start, again, that is simulating, when the client is moving towards the server. So it's probing, didn't receive the ACK in time. It's still resuming search, and will do that until it, actually gets there. Then the ACK is received. Because,
we can see the server, not the client.
Oh, I'm showing the second one. My bad. Actually, that's. Oh yeah. Let me start share. Okay.
Yeah, you might need to share the full screen. Maybe easier. Yeah.
Okay. Is that? Can you see that now?
Yeah.
All right. All right. So again, going back, as you can see, I'm highlighting this up. For the first 5 seconds, or or 10 seconds actually in this case, we are kind of simulating when the probing is happening. So, the client is moving towards the server. We did this by just, putting up sleep timers just to make sure we're kind of simulating that before we are actually getting the first communication from the server. So we're waiting until we get the acknowledgement from the server. And after that, we got our acknowledgement and we start the communication. Once we start the communication, a shadow object has been created on the client, as you can see over here, because we're requesting the file. And again, we kind of creating a file through that shadow object using the create function. Then again, just to confirm that the file exists, and that's the f handle of that file. Then we are sending a new file or sending that file to the server and basically just saying, hey, that's my first file. And then we're zipping it. This function shouldn't be in client, but since it should be from the sensor side, but since we're only implementing a master and a client, we thought it might be beneficial to show the function at least. That's how we're doing it. So as you can see, we go for the current size. We look at the type, that's CSV, and then we take a look at the zipping algorithm that should be used, and it zips it. The interesting part about zipping is that you can still read the full file after zipping, because after zipping, you still have the pattern and the partial data, and you can kind of, recreate data using that. And assuming that the centralized server already has the computational power to run high-end models, high-end machine learning models, it should be able to recreate the data at least. This way it will have more data, but the computational time might increase. That's a trade-off that we're working with. And in some of our future work, we plan on optimizing that. And here's us updating the file. Again, we're just checking the file is updated. And I'll show you the server. Again, you can see it here on the dump.j just to check hey, the file has been updated. And yeah, those are the functions that we created. And that is, our demo.
Okay, that's great. That's great. Thank you. Thank you for your hard work. And I think it's interesting. I think let me ask a few questions, because I'm really interested in the detail and how this will be applied. I mean, in my mind, immediately I have one question is that, do we assume the file size in the applicability of such protocol is going to be reasonably small? Reasonably small, like in your example, is a 4 megabyte, right? 4 megabyte. I think 4 megabyte is probably okay. 4 megabyte already can send a very short video or some image, okay? It's not going to be like anything bigger than 100 megabyte, I'm assuming. That's meaning that we're dealing with a reasonably smaller file. Okay, and then if I'm going to send a big file, say a surveillance video, I'm going to break them into smaller video chunk and then be able to send it. Okay, so that's number one. I just want to clarify. The other thing I want to clarify is that what do you think that we have a multiple client simultaneously joining a single cell, try to do a file update? What's your assumption over there?
So right now, again, this, like I said, we didn't have enough time to think about that particular scenario. But the current assumption that we're working with is that we only have one client. But in the case that there are multiple clients, the protocol would need to kind of make a queue system, at least the way we discussed it, like having a queue system that only one person can actually go ahead and do it, especially since it's networkless, right? Having multiple people, or let's say in the worst case scenario, you have 8 people on the same server trying to make a connection via Bluetooth. That's going to put a lot of strain on the central server. So we might as well make a queue-like system over there. We weren't able to implement this for our demo because of time issues. But again,
it's okay. It's perfectly, your demo is more than enough. I'm just talking about the concept about what you're doing. The thing is, you use the term real time. You use the term real time, that means we want to be able to handle this kind of requests in a short period of time. I mean, it's because real time has one property, and the other thing is that you might the client might be moved away very fast. He's moving. He's actually moving across from one server to another, maybe. So that's why we want to do it as fast as possible. But the other thing which I'm also thinking is that if I'm going to handling multiple clients in this scenario about updating file or reading the file, what do you think is going to be the bottleneck? It's going to be the network layer, or it's going to be the system layer, like an operating system, the software?
I think it's going to be a network layer in this particular scenario, mainly because the central server, the operating system should be able to handle multiple requests. But then again, in the networkless part, to my understanding, the idea here is that if you have multiple people, right, it's a network that constricts the data, at least from where I'm seeing it. Because again, if you have too many people over there and like the central server cannot handle that many network requests, or the bandwidth kind of just drops down, or like if you have Bluetooth, if you get interference from multiple other, clients in the same area, that's going to cause issues. At least that's what I believe. But yeah.
So my understanding, Wi-Fi might have a more issue with Bluetooth. Wi-Fi, I think everybody using the same, whatever, the megahertz, everybody is sending into that. You might have trouble with one single base station. But Bluetooth, I understand that they have some kind of picocell feature that you can actually reserve. So Bluetooth actually provides some kind of quality of service for different, so it will entertain different connection. So Bluetooth might be a good choice to handle the real time.
The issue that comes with it is that you can only have so many Bluetooth ports, because again, the whole idea is that you're preserving the whole connection, right? You're preserving like 2 ports between 2 different clients, and you can't do that for a lot of clients, because again, I forgot the name of the type, the style, but it's the same way like phone. It's similar to how phone connections are made, and you're kind of just fixing that channel. You cannot fix a lot of those channels because again,
I think there are some limitation of 8 or 16. Yeah. I forgot. By the way, just to let you know, I actually implemented the first generation of Bluetooth protocol in around 2000. So I actually implement the congestion control, but Bluetooth has changed a lot. That was Bluetooth 1.0. I did the implementation in the link layer management and encryption. It was a fun for me to just have fun to do that. That's why I know a little bit about that. They actually guarantee some kind of performance there in real time. So I think because we're talking about the scenario, it's really important that if we actually assume this is a sensor environment, we only have a small number, say less than 8, then I think this should work well. It's just when you talk about the real time, when you use the term, by the way, I want to ask you, when you use the term real time, what's your definition of real time? What kind of things do you want to require?
Yeah, that is true. We should have kind of expanded on that. When we say real time, we basically mean the data is being gathered real time, but the data that can be accessed from the central server doesn't have to be real time, because that depends on the person when they want to access it. Okay. So the data stream between sensor and the client is constant, or not constant, but like near constant. It will always be sending data until the data gets full, or the central server gets full, or say like, hey, we don't need any more data.
Right. Okay.
But the client is kind of, it depends on the person. Like, hey, the client want to access the server right now, and that's our definition of real time. Like it's not exactly real time between the central server and the client, because that cannot be real time. Like you cannot have a constant stream of. I mean, you can, but again, you cannot have multiple of them just sitting there and just doing like accessing the data all the time. At least not at the same level as the way sensors and central server does.
Right. So you're basically saying that the central server is pulling the data or updating the data from the sensor. The server is basically as soon as possible, and basically is collecting there in the central server, and then the client, based on its request, is going to try to pull it out. Yeah.
Yes.
Okay. That makes sense. Yeah. That's an important application scenario. I'm just thinking that when you talk about this NLFTP, networkless FTP, I'm just thinking that the design, for example, you say 3-way handshake to 2-way handshake. So essentially, you actually want to design a new transport layer protocol. My question is, why not? I mean, why not just use either the existing protocol like TCP UDP or DCCP? There's a few
Yeah.
newer transport layer protocol. I mean, I guess you have some reason considered to do your
We
own.
do have a reason. The whole idea, we looked at TCP and UDP. We were kind of, what's the word for it? We were kind of confused that why, again, like UDP would be a great choice for this, but then we realized that UDP doesn't guarantee anything. UDP is a guarantee less, at least that's, again, from our readings, we're like, hey, it's mostly guarantee less. You're not going to get any guarantees on the data that is on your central server, which would work like if you can, get all the data back again. And again, in our definition of real-time system, works great. But what if there are files that are like, that takes a long amount of time to collect? For example, the data for a whole day's worth of, activities, right? You kind of merge that in a CSV, and if you lose that data under UDP, well, especially like since there's a higher chance here now because you can only communicate in a circle and it's dependent on the person. We felt like that might be a huge loss to the whole system, and you're losing important information. And other than TCP, we just figured that TCP is too heavy for this kind of system. We were like, you need a three-way handshake. We might be able to implement that in the future. But, the whole idea was that a three-way handshake again, and then like the whole heavy part where you are doing congestion control, you're doing packet loss stuff, it kind of forces the user to be there in that circle, and they might not want to be. So for example, if you do this in like
I think you don't want to use TCP because TCP built in a lot of congestion control, which in this case is one hop. You're not going through the internet, so it's wasted to do congestion control. UDP, you might have a chance to detect any loss in the application layer. In the higher layer, you realize you missed that, and then you can potentially request just that packet. UDP is try to just be really, really almost close to a raw socket. So it's really inexpensive. Yeah. It's interesting. I'm thinking every time I think about this new application that you're talking about, I'm always thinking about whether we should redesign the transport layer protocol. There is some advantage, but before you do the redesign, you want to be really clear that you're going to get that advantage.
Yes.
That with this design. Okay.
Professor, I would like to share some of the future works that first I think I discussed most of them, but just in case I missed any. So again, these are the big three parts that we kind of we discussed when we were coming up with this idea. We want to optimize the process of the NLFTP such that dry transfer can keep copies of the packets. This kind of relates to your idea, your comment of saying we want to make sure only the delta can be changed. So if you can keep the changes in smaller packets, if you can detect the changes and keep them in smaller packets on the client side and then send them, the whole copy process gets a lot easier because now you can just transfer them. Something akin to how a GitHub pull request works. That's how we were thinking about it. The duplication process is a big hitch in our system because, again, if you remember, we said that we want to make sure that the duplication happens properly to kind of make the system robust. But if there are multiple clients and multiple clients are requesting multiple files, there might be too much duplication, and that will kind of make the system fill the system at a faster rate. So that is another thing that we want to focus on. That is multi-clients, having multiple clients in that system, and how they access the files. And again, that's the third point too, update and create rules and how they actually interact with that system. But yeah, for this particular part, we kind of just created the protocol or the basis of the protocol, but there's a lot of work that needs to be done in this part.
Okay, thank you. This is great.
These are references.
Hold on, let me see what did you referring to? Okay, Vincerf's paper. That's very classical.
Yeah, we went over TCP and UDP. We kind of had to refresh our memories, and we were we are dealing with TCP, so might as well go for the classical papers.
Okay, that's great. Yeah. Okay.
All right.
Okay, so I don't have any further questions. I think I should move to the other group because they have been waiting for a long time.
Professor, I do have one question before we go.
Sure.
What about homework 2 and homework 3? I believe
your group hasn't been graded, right?
Yeah, but like we don't even know when to do that. Like we thought that the TA might.
I haven't checked. The TA is supposed to send out the Zoom link for people to join that channel.
Yeah, we haven't gotten anything so
Okay,
far.
let me check again. I'll send the announcement after I'm done with the demo today. Okay.
Right. Thank you.
Yeah, sorry about that, but we'll get there. Yeah, the next group, please. Now you can.
Sure.
So just let you know, the 2 o'clock group, I'm sorry, there is a delay. We're going to, if you're for 2 o'clock, we're still doing 1 o'clock. So one more presentation, then we can go to the 2 o'clock. Yeah, go ahead.
Sure, let me share real quick. Claudia, do you want to, I guess, start it off?
Sure. All right. So our project is the Social Package Manager, and it's about using your social network to verify the trust of packages you install. And specifically, we're focusing on the Python ecosystem. So our problem statement is essentially that package management systems generally allow nearly anyone to submit a package. Granted, there's, depending on the repository, some form of review. But there have been cases before where this has been spoofed by malicious actors. So our problem is, how can we see whether a package you install, in this case for your Python ecosystem, is something that's trustworthy? And so taking an ethic OS approach, we built this tool that uses a distributed hash table to store what packages you have installed and share that with your network. Stefan, would you like to continue with the details?
Yeah. So I see what you're saying. So in our database or distributed hash table, we have both a network, so connecting people together, and then each person has their list of packages that they've installed. And the idea, or I guess the idea sort of motivating this is that people if they have packages installed and they're people you trust, then it's more likely that packages that they have installed are, going to be more trustworthy. So in this example, so ID1 has a network where they're connected to ID 3 and 4, and then IDs 3 and 4 have networks sort of extending beyond that. And so if person 1 in this case is looking to download a new package, they can go through their network and see if people connected to them or people connected to their connections have this package and get an idea of whether it's safe. And like the closer in the network you are, I guess the stronger the connection and the more likely you are to trust them. And then like the farther out you get, sort of the less trustworthy, I guess it is. So this is all based on a distributed hash table. So it's, I guess, in many ways like a regular hash table, except it's sort of distributed among, or I guess distributed. So within our hash table, we have, or everything is keyed on an email address. This is, I guess, our way of, making sure you know the person you are like connecting to. So if you know their email address, you can hash that email address and then find their entry in the hash table. And then, so within each entry, you have your name, so just some sort of identifier. You have your list of friends, that's your list of keys to link to other entries. And then you have your package, your list of packages. So one thing we didn't have time to implement, but we were looking at is protecting the key entries with either symmetric or asymmetric cryptography. So OpenDHT, which is the open source implementation we're using, supports both of those. And so that'd be an easy thing to sort of add in. That's strange. Okay. So I guess, David, do you want to talk about the social score? David or Claudio. I'm not sure.
David,
I think
you're
David's
muted.
muted.
Oh, okay.
Okay.
Yeah. So for the social score, there's supposed to be an infographic to the right that shows like the output of the program. So the social score is based on your social network, based on your friends who have the packages. The more friends you have, that package, the more trustworthy it is. It's kind of like a score per se. So friends that are like closer to you, like one jump away, are more likely to have a higher weight in terms of trustworthiness than friends of friends, which is like 2 jumps away, and so forth. So that we put a weight of 1 over n, where n is the degree of the connection. For this project, we limited to 2 jumps, just for if you just keep going down, it's just the cost of just calculating the hash table is just too much. So yeah. Oh, you want me to keep going?
So I guess I can pick this back up. So we also just generated like a general package reputation score. So this is like another source, like another sanity check that goes along with your social reputation score. So this is based on a GitHub repository associated with a package. So you're basically looking at how reputable it is based on stars and forks. And I mean, you can also look at other statistics. Those are just the ones we were looking at. And we started with Python, but similar things can be done with NPM, so the JavaScript language with Cran and R, or Maven with Java. And then from here, we're going to go into a demo. So should still be able to see that. So we have this running in Docker. We have our hash table sort of running in Docker, and we have 3 nodes set up right now. So we have this is or SPM, so the social package manager is our command, and then if we run tree, it sort of shows.
Should bootstrap the DHT again.
Yeah. There we go. So it shows you your own packages, and then your first connections, second connections, and then further down, but we stopped at 2, and also just those are all the people we added. So it shows you your connections, or your packages, your connections, and then your connection packages, and so on. So if we, this was Dr. Wu's, this is Claudio. So if we run his tree, we see sort of a similar hitting thing here. So starting from Claudio here, but you can see, I guess, the same idea. And then, so if we have, this is David, and oops. So if we have, so he has not added any friends yet. And so if he wanted to say, look at JSON RPC, so if you wanted to pip install JSON RPC, he'd see that there's no one in his network with that package, and has a social score of 0. Also has a GitHub score of 0. There's nothing on GitHub that matches this. So he's prompted, are you sure, do you want to proceed? And he's going to say no in this case. But he does know that Claudio has JSON RPC on his system. So if he adds SPM add Claudio, is it just Claudio, or is it your first and last name?
No, it's my email, stevie.spees@ucdavis.
So if he adds him to his network, and then we look at his tree again, generate, there we go. So now we can see that Claudio's network has been added, or Claudio's tree has been added. So now we see JSON RPC is here. So if we try pip installing JSON RPC again. So now we have a much higher score. So we have a first degree connection. So JSON RPC is a first connection. And then we also see that a second connection, so one of Claudio's connections, I have JSON RPC installed. And so now we can see that this is a much higher score. And so it's much more likely that it's going to be a trusted package. And so I want to install it this time. And so now if I run SPM tree again, so I can look at all my network and all my packages. So now I can see that JSON RPC is now in my network because I just installed it and based on sort of this reputation score. And so if we look at Claudio's tree again, we can sort of see that now David has this new package installed that's sort of propagated through the distributed hash table. Claudio, David, am I missing anything for the demo? I think that was...
There is a feature that you can see the packages of an arbitrary user given their email.
Yeah.
Say if you wanted to consider whether you wanted to add, for example, Dr. Wu as a trusted source, you could see what packages they have.
Yeah, so if I...
Even if they're not in your network?
Yeah, before I add someone to my network, I can just look them up and see just their packages to see if they have something that, or if they have some sort of package that I think is interesting or useful, and sort of see what their node or what their entry looks like.
Just to let you know, you used the wrong email address.
For you?
No, my email is wu@cs.ucdavis.edu or sfwu@ucdavis.edu.
Okay.
It's a wu@ucdavis.edu. That's our elder son's email address.
Okay.
He took a course at UC Davis and get that email address. And after a few years, he left. Of course, he left UC Davis a long time ago. And I tried to get it back, and he said no. He wanted to keep that. Just to let you know. Okay. Yeah. Okay. So great. I mean, I'm really impressed. So I'm going to ask you first clarification question. So you implement the SPM, right?
Yeah.
SPM is your tool. And when you did the command SPM pip install certain, is that installation is like just demo fake, or is actually trigger the real implementation, real installation on this? I assume is a Linux system.
Can I answer this question?
Oh, sure. Yeah, go for it.
So yeah, I did this part of the implementation. So the idea behind SPM is that it's a form of wrapper. You would prepend it to, like, instead of doing npm install, pip install, you do SPM, then the package manager, and then the rest of the command.
Right.
And what SPM does is it looks at your first argument to determine which package manager you've given it.
Right.
And in this case, we've only done a pip. If you type, for example, SPM space npm, it'll say this package manager is not supported yet. And what it does, or what it should do, is it takes all of the remaining arguments. So install JSON RPC, for example, and creates a sub process. It forks and runs pip with that command. However, for this demo, we've commented out that line of code and put in a sleep 2. So yes, it does work. But for the reliability of the demo, we commented out that line of code. But yeah, it's in the code. So it would work.
The reason I'm asking that question is I'm really interested to use the system as a user, especially with a group in the class. For example, undergraduate EC36B, I'm going to teach in the fall. I would like to, because you can imagine, I asked the student to install RPC, JSON RPC, and install package. It would be nice that we actually know each other, what you have installed, what you don't have. But this has to run on Docker, right? Or any environment.
It can run on any Linux environment. The reason we've done it in a Docker is twofold. First of all, using Docker Compose, they're running in their own little network. And we have tested it over the wider internet before. but the hash table retrieval is faster on a, one network on the machine.
Right.
And the second reason is that we had difficulties compiling OpenDHT for Mac OS, so that the package is not available pre-compiled for Mac OS. So we decided, for the sake, since David actually uses Windows, I use Mac, Stefan uses Mac, that I just Dockerize everything so that the Docker container builds this library.
No, I like Docker, actually. I like Docker because we can standardize, especially for education. I'm actually thinking about what's the possibility of using this in an academic environment. And using Docker, as you said, that's actually really simplify a lot of things in terms of implementation. Okay, so I feel to look at the tree to understand what package has been done, I think that's very useful, very valuable. And I feel whatever you have built is actually not too far away from something which we can actually deploy for real user. That's great. I'm really impressed. So now I'm going to ask you something which is more a bit of intellectual part of this. So when I look at your system, you're sharing information about what you have installed. That's one application. But the same mechanism can actually apply to many other information. For example, which email that you have read or which URL you have visited. Is that safe to visit this, or which kind of piece of information that a user or your friend has access? So here actually turning to a deeper level question is privacy. So it's probably okay for me to share with all my students what package I install, but it might not be good for me to share all the URL I have ever visited. So in other words, I'm actually thinking that whether it's possible, I'm still having this kind of social network idea, but I only use a social network internally to calculate the trust score. So when I actually see this, I don't see exactly who actually access what. But I know when I want to access this URL, I want to actually see what's the score in my social network. I only need to know that part, but without knowing who actually access what. Do you think it's possible to actually do this with DHT?
So I just want to make sure I'm understanding that. So it's I guess in your example for websites, so you want to be able to like calculate that website score. It's you just it's just so, but no one can see who visited which website. So like if 5 of my first connections have visited, I know that's like because of my score, I know it's a trustworthy website. I just don't know like which 5 connections.
Right. Okay. Something like that.
Yeah.
So that, well, I was thinking when you first present the slide, DHT, I'm thinking it might be hard because it really depending on where you're going to calculate the score. Who is going to calculate the score? If I'm the client, I'm going to calculate a score, then I need to receive all the information about the social network. The issue about social network is that it's a network. It got distributed to a DHT, but the thing is that only I know which node is actually 1 hop from me, which one is 5 hop from me. And the thing is that DHT itself is just a general network and it doesn't serve as an individual user. So that's what I'm thinking. How do I actually, I might still use DHT, but I wonder whether there is a social network version of DHT, I'd be able to calculate the score in the DHT environment itself. Because once I actually get all the data to my node, then people's privacy is potentially revealed. So I think if you can solve this problem, then this is going to be a very powerful general mechanism for almost everything. I mean, let me give you an example. If somebody actually send a scan, and when he send a scan, he's not just sent to one person, he's going to send to all your friends. For example, my account get compromised, all my students get an email. So if one of you didn't look at other people, you might think that, oh, okay, this is Professor Wu, and then I have to trust it. I wire $1,000 to this account. But if some of you actually realize this is a scam, then you can put that score, and immediately other people will get alerted that, hey, this email is actually a scam. So it's like using the social relationship, because it's very easy for Stefan know I'm actually in Davis, I'm not in Ireland. So, but other students might not know. They thought I'm in Ireland, you know, lost my passport or something. I need somebody wire me $1,000. So I'm just thinking that this potential scenario has a much broader impact. It just need to solve this problem with the privacy issue. Yeah. Okay, this is great work, and I really love it, and I hope to follow up with you with some of the detail for software package, not the second part. I really want to talk to you whether it's possible to be able to continue in a way that 6 months from today, a undergraduate programming course that's a student need to install package, they can actually see what's going on. And it's actually perfectly for me as an instructor, because I can easily know the progress of the student by looking at what package they have installed. If they haven't installed certain thing, I know they haven't, they're behind, so I can probably harass them a little bit to ask them to speed up. Yeah, but it's great work. I really like it, and I think this is great. Okay, thank you. So I'm going to continue the next group. I probably will follow up with you privately. Okay, thank you.
Great.
Thank you for all your work, David, Claudio, and Stefan. This is fantastic. Thank you.
Thank you, Professor.
Yeah, thank you. You're welcome. Okay, next group. Sorry for the delay. So next group will be, let me see, Zan, Kunlin, Weijia, and Shi. Is that right? 4 of you are in the same group, right?
Yeah.
Okay, thank you. Yeah, go ahead. You can share your screen.
Okay, I'm gonna share my screen.
Are you doing the same thing? Package tracking system? Is this a software
Yeah,
package?
but not
or real?
we're doing the actual logistic package, not the Python.
Like
package.
a UPS kind of
Yes,
package.
yes.
Okay, good.
Okay, so our system is a package tracking system. I'm gonna go straight to the problem statement. As we know, the global pandemic has been going for over 2 years, and recently we all got a feeling that such as you do online shopping, and the delivery date is always the delivery is always going to take you longer and longer. The estimate delivery day is always going to be tomorrow, but it's never going to be today. So we also did some research that it shows that the global air cargo capacity and volumes has been fallen significantly, and with the lack of workers in the logistic industry, many packages information would often go wrong or even get lost. So we are doing this package tracking system, which allows clients to get their locations of their packages whenever they want. It uses multiple replicas to store the information to make sure that the information will not get lost. So it has some kind of robustness. Okay, let's take a look at this system design of our demo. We have 2 sellers, which is responsible for sending out packages. And we use the 3 replicas to store those package information. And we have 2 flights. Each plane will be responsible for loading and unload the packages. And every time the airplane took off and landed at a new location, it will update the package information to all the replicas. And as for the client users, they can send a request to the replicas to get their package information. In our demo, there are seller 001 and seller 002. And for seller 1, it has sent out 3 packages with the destination of Alaska. And for seller 2, I should mention that this destination XX it represents any other place except for the 3 states we have mentioned here. It's just
may I ask a question? So seller 1, the package 2 is from New York.
Yes.
So essentially, I don't have to be. I mean, each seller could selling from different location. Is that right?
Yes, because in our understanding, each seller can have different warehouses in different locations.
Right. Okay. Makes sense. Yeah.
Yes, and okay. And we also have flights 001 and 002. Flight 1 is traveling between California and New York, and flight 2 is traveling between New York and Alaska. So the whole process is like this. You load the package 1, 3, and 100 from California, and the plane 001 took off and landed at New York. And also the 3 packages will be unloaded at New York. And at this time, the package number 100 has finished its traveling. But the package 1 and 3, their destination is Alaska. So they'll keep their trip from New York to Alaska. Using this flight number 2.
Mm-hmm.
So that's basically the whole process of the 6 packages.
Okay.
Okay. And we'll show that in our demo later.
Okay, sure.
And as for the future design, we're thinking about some privacy issue because as for now, the checking data process, it will show all the packages with no distinguishing the each users, such as user 1 has its own package and user 2 has its own package. But for example, user 1 has ordered package 1-3 and user 2 has ordered package 100. But when our demo do the check information method, it will show all the packages, which means there's no privacy as for now.
Okay.
And the second thing is we're trying to implement algorithms to assign packages based on traffic or time or the flying cost to determine which warehouse we should be checked out.
Can you go back, before you do the demo, can you go back to an earlier slide? I want to take a look at one thing. No, go back, go to, I think the second slide or the third slide.
Is this one?
Yeah, I'm actually trying to think about. In this example, what do you use? How do you actually use the replica? What is the replica is actually helping you?
Just like the Google file system, such as we each time the packaging location has been updated, it will push the update to the primary, and then the data will flow over the 3 replicas.
To other replica. Okay.
Yes.
It's just a duplication to provide some kind of robustness into the system.
Yes.
Okay.
Yes.
The other question for you is that in this picture, where do you decide which package go to which fly? Is the fly actually decide? The fly actually read the primary replica and then decide whether it should load and unload certain package. Is that right?
That part of the implementation is actually done by Jen. Can you answer that?
Oh, yeah.
Jen? Okay.
For this part, actually, the flight will load the package, and then, but it's not automatically assigned by the computer. It's actually just flight loads some package. I can show the code. Can I show?
No, I think later. Yeah, you can either show the code or do the demo together. We can take a look. But my question is that just think about the programming part. Is that I assume when seller 1 and seller 2, or when the client they want to, okay, let me actually use this question to understand each of the component that we're talking about. So the client access the primary replica to understand the tracking information about like where is the package that's being delivered to me. So seller 1 and seller 2 essentially push the package into the primary replica as if it's actually put the package to the airport, to the
yeah, the data stored in the primary replica is the package ID and package right now position and its destinations.
Right.
And
right.
then the seller only push the package. It says, I'm selling this package. And right now this package is at where, and where is its destination. And then the flight will load the package. So the seller won't let flight load that package. There's no algorithm automatically let flight to load the package. Yeah.
I'm just thinking a more complicated situation. There is a decision that needs to be made that the fly 1 or fly 2 should pick up a particular package, right? There is a, because when you're talking about a more complicated, I mean, your example is probably okay. It's only 2 fly, and they're not even in the same. They're not actually. They're totally just connecting fly, right? From here to this and then connect. But more complicated, I think it will be some distribution center need to make a decision about which fly pick up which package. But right now, I think your implementation is fine. It's just fly 1 will be load whatever the destination. It's the same as the destination, or actually source. I mean, in a particular airport, if I'm flying from New York, then all the New York package should get onto this plane, essentially. Yeah. Okay. Okay. Fine. Yeah. You can do the demo now. Yeah.
Okay. Let me start sharing.
Sure. Let me show the. I think this one. Can you see my screen?
Yes, I can see your screen.
Yeah, we like our homework assignment. We first run the mini GFS, like the replica. Oh, sorry. then because these three actually are in the same level. Oh. So I just make the primary wider to see what's happening in primary.
Yeah, that's good. That's good.
Yeah.
That's smart.
And then I wanna go through our here is our program, like seller package their package, send it to the data center, and seller too, and then our flight will load the package, and then when it landed, will automatically update all the package to it, and then the seller check the data after. Whenever it wants, I just put seller check data here. You can anywhere, or you can compare it in other program. That's okay. And then so and then run it. So like here, first three is that the seller one will package some package, tell the data center that he has some package to send. He load package 1, 2, 3, and then in the center tell her there are 3 packages right now, 1 or 2 delivered. And then this is when seller 1 do the checkout, it tells him your package 1, 2, 3 still in delivery, and they are from CA to AK, and there's right now position and their destinations. But right now they haven't been loaded by any plane, so there's is right there and then changed. And then the seller 2 do the adding package and checkout. But here is what we said, that we didn't do any privacies. We show all the packages in the server.
I think that should be easy to do. You just need to set up a customer ID, and I only show whatever that customer ID related to that customer ID. Yeah. And
then here is the flight loading package. If it's good, then it was successful. Loading package means this package, right now this flight is from California to New York. So any package is at California, it will successfully loaded. And then when the flight, here is flight checkout. So it's already loading 3 package. And then here is this flight 1 took off. When he took off and then landing at New York, it will come back. So it's now it's from New York to California. Then we can check that its loaded package is none and all the package position has been changed. And because here the package 100 is already delivered, so it's deleted from the server. So because it's already been delivered. The same as the flight 2 and the package things, and some package has been delivered. So the package undelivered on the server are becoming smaller. And then here is the seller. When seller checked their data, they found that seller 1 found that his package 3 is still under delivering. The package 3 is at New York. And for the seller 2, he found that the delivery package is 101 is still under delivery. And yeah, that's basically what we do.
Okay, can I go back to your code? I want to just tell you that what I'm talking about. Go to the run, run.cpp. Can I add a flight?
Yeah,
add a flight called flight 3.
So it's flight ID and it's
right. So maybe flight 3 and flight ID is going to be 003. And it's going to be from New York to California. Okay, and then I actually want to do, oh, right now you're basically loading package over there. Okay, because you're actually manually in the run to do that. Because I'm actually trying to add a line 30. If you add the line 30, I said flight 3.load package, whatever. I would say load package 1.
Okay.
Okay, what do you think will happen?
Let me see, because right now it has already, flight 1 has already landed at New York, so the package one will at New York, and it will load the package. But
can I go back? Can I go up a little bit? I want to see the flight. Yeah, flight. You see that flight 2 and flight 3, they're both from New York.
New York, yes.
So flight 3 kind of snap it and then send it back to California. No, I'm just saying that, yeah, it's because there might be a California direct flight from California to Alaska that way. But if I do that, then what will happen? Flight 2, because the package is already being taken out, will that function? So what I'm saying is line 32, what will happen to line 32? If I have a line 30, what will happen to line 32?
Oh, I think yeah, I think right now both of them were loaded that package in my code.
Okay.
Yeah.
All right.
But whenever one flight was land, then the package destination will change. So when the flight 2 landed, this package won't change that position.
Right. So your program, you didn't check whether the package is actually still there.
Yeah, basically load package and landed, they were in the same. I mean, what we were going to implement next is that automatically assign which plane load what package. So
well, it's okay how you assign, but the question I have is that when you decide to load the package for a flight, I think it need to check whether the package is still there at the airport at that particular location, right?
Because right now these 2 planes are all at that location, so they can load it. They all can load it.
Okay, then, well, they load it, but I can say,
like here, if you add a line, like,
can I add like a flight 3 landed? Yeah, that's what I'm saying.
Here, then flight 2 cannot load it again. Because
that's what I'm saying. If it's a landed, then it cannot. Yeah,
you cannot. But if you don't have this line, which means these packages are still at New York, then both of them.
I think what you should do is that whenever the flight departure, not landed, but departure, when they already took off in the airplane in the air, that package is no longer available, right? For next week.
Yeah, we don't have the function called departure. We only have landed. So maybe departure and landed are.
It's okay. It's okay. You can actually fix that. Okay, that's a fun little experiment that you're doing. That's great. Okay. Thank you very much for your demo, and this is interesting. It can certainly be develop more. I'm just thinking, instead of having the flight, I'm actually thinking there is some application for the same kind of system for delivery. And the delivery is not necessarily used by this kind of big carrier like whatever, Amazon, or they're doing, or Federal Express, they're doing this delivery. I'm actually thinking this kind of system may be useful for us as a campus environment to actually just deliver something among ourselves as a friend, to actually be able to help us to share stuff, share food, or share whatever gift. And it will be interesting to kind of think about how can we actually do a delivery local environment using this kind of tracking. And the tracking, we can actually see when we're going to get this. Okay. All right, this is good. I like this, your demo and the problem you're working on. Okay, so now I'm going to stop recording and then I'm going to move on to the next group. Okay, thank you. Thank you very much.